So in the previous unit, whoa, that was crazy. Okay. In the previous unit, we looked at, say, titrating silver with chloride until we ran out of chloride, yes? What color precipitate? It was a white precipitate. Do you remember, because I had you go and watch this on your own, do you remember the ion that we also added in as an indicator that would react with the silver once all of the chloride was gone? Yeah, I know. That's how I feel about it too. I am asking the question going, nobody remembers it. Nobody? Yeah? Chromate. See, she remembers. Damn, nice work. All right. So our indicator was chromate. And basically the silver prefers to react with the chloride. It precipitates more strongly with the chloride. So until all the chloride is gone, silver will not react with chromate. However, once the chloride is gone, you get Ag plus, two of them, plus CrO4, 2 minus, and you get a precipitate of Ag2CrO4, solid. Anyone remember the color of that precipitate? Red. So you're like, oh, red. That means my reaction is done. That means all the chloride is gone. Yes? So that is an indicator for a solubility equilibrium. And we're just mentioning that because we have not yet done our test on that, so we are reviewing that concept for you. Okay? Now, an acid-base indicator is a wee bit different. It is actually a weak conjugate acid-base pair. It has to be weak, and it has to be the pair. It's not just a single substance, it's actually two substances. The acid and the base. It has one color in its protonated form. So maybe HIN is yellow. And it has a different color in its unprotonated form, which means we take off the H plus, and maybe that form is blue. Now, every indicator, every acid-base indicator changes color at a specific pH or across a specific pH range. And we've got a table for that, which I will show you in just a few minutes. For now, I'm going to show you a very complicated structure. This is brom-cresol green. These two together make brom-cresol green. Okay? You are never going to have to know that entire formula. That would be crazy. Yes? What you should know is that one of the forms has a hydrogen, and that particular form, the acid form, is yellow. Whereas if we lose a hydrogen, It's now not going to be yellow. This form of it is blue. So that is the base form of the indicator, the unprotonated form. Now, indicators, because they've got these big, long, complicated formulas, we might call bromcresol green HBG, where B stands for bromcresol and G stands for green, okay? And BG minus is just bromcresol green. Now, you might we often refer to the acid form of the indicator as HIND or HIN, where that just stands for indicator, yeah? We might refer to the base form of the indicator as IND minus or IN minus. So we'd often just use generic sort of formulas for them. Like we used HA for an unknown weak acid, we'll use HIN for an indicator, or HIND. And this just reiterates that we don't bother learning the big structure. Notice that I have been bolding and capitalizing pair when referring to the acid-base indicator. It includes both members of the acid-base pair. So the indicator is both together in equilibrium with each other. So bromcresol green itself is HBG and BG minus together in an equilibrium mixture. Bromcresol green is not just HBG, nor is it just BG minus, okay? It is both of them. The acid-base pair has to be weak so that you can have why is it moving around? So you can have an equilibrium. You need to have an equilibrium because we need to be able to shift from one color to the other color. So it's impossible to have an indicator that is strong because otherwise it can't shift back and forth depending upon the conditions. Oh, that's fun. Why are you way over there? Can I move you back? Okay, let's try that. Okay. Dear God. Okay. So here we have bromcresol green, and we have the acid form, which is yellow. And we have the base form. Actually, I shouldn't highlight this one yet. We have the acid form, which is yellow. And we have the base form, which is blue. So if we were to put this indicator into an acidic solution, in an acidic solution, concentration of hydrogen is high. And if concentration of hydrogen is high, what does that cause this? Why is it making like weird shapes? I'm trying to make an arrow, you stupid little pen. There we go. Okay. Which way is it going to shift if we have high hydrogen? It's going to shift to the left, which means, so it is shifted to the left. That means, what is the concentration of HBG going to be like? Is it going to be high or low? HBG is going to be high, and BG minus is going to be low. So we can say that HBG is the predominant species. You need to know the word predominant. It does come up from time to time. It just means main. So it is the major species present, okay? And if it is the major species present, the main species, the predominant species, what color will the solution be? It'll be yellow. Why is bromcresol blue? Why is bromcresol green blue in basic solution? What do we have a lot of in basic solution? OH. What does OH do to this equilibrium? It reacts with H. Yep. Okay, so we have lots of OH present. The OH reacts with H, so we get H plus OH minus gives H2O. And that causes the hydrogen ion concentration to increase or decrease? Decrease. Which will cause the equilibrium to shift to the right. And if it shifts to the right, who is the predominant species? BG. And so the solution will appear blue. Okay, I think I've got blanks for that, but I don't know that it's that important. The system shifts right. You can fill them in if you want to. HBG is low. BG minus is high. Therefore, BG minus is the main species. What is that word we use for main? Predominant. Species present. And the overall color of the solution will be blue. Now, the word that we use when an indicator is changing color is that it transitions between those two colors. So it occurs when you have the acid form, but you also have the base form. Okay, so you're not like all blue or all yellow. You've got some of each. If they're relatively similar in concentration, it's going to be changing from blue to yellow. So the transition occurs when the acid form and the base form have similar concentrations. So yellow and blue have similar concentrations. What color will bromcresol green be when it is transitioning between its acid form, yellow, and its base form, which is blue? It will be green. And now, just because every year there's at least one or two people whose kindergarten teachers did not do their due diligence and teach people color combinations, we're going to go through yellow and blue make green. What about red and blue? Purple, yes. And what about red and yellow? Orange. If you are one of those people whose kindergarten teacher did not do a good enough job, then you are expected to memorize these. Okay, if you already know them, then you don't need to memorize them because they are just part of your knowledge from your childhood. Okay? I know it's shocking, but every year there's like one or two, and I'm like, Although, I do have to say, I had a student one year who didn't realize that he was colorblind until we were doing some graphing, and I was graphing one of the lines was in red and one of the lines was in green, and I'm like, you can see the red line is blah, 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 and you can see the green line is blah, blah, blah. And he's like, those two lines look the same. And I'm like, oh, hang on a second here. So people often don't know until later in life. So if you're like, these two lines look the same to you, then you should go and check with your eye doctor, okay? Because you are missing some particular receptors in your eyes. All right. What is this thing? Okay, whatever. I'm just going to go over here. That's fine. When the acid form is exactly equal to the base form, okay? So when we have our acid form, in this case yellow, is exactly equal to the base form, so that would be the concentration of the HBG is exactly equal to the concentration of Bg minus. We call that the transition point. Which we can abbreviate TP for the indicator. It is when the color A is equal to the color B. Concentrations of both those colors are the same. So you should know the definition of the transition point. It is the point when HIND is equal to IND minus. And do you remember two other points we had during a titration? During a titration, we had an equivalence point. Which is the point in a titration where the stoichiometric ratio is perfectly fulfilled. We have an end point which is also the point in a point in a titration. And it's where the indicator changes color. So those are points in a titration. The transition point, technically you don't need to be doing a titration or anything. It's just the point where the two colors, the two forms, the protonated and the unprotonated form are equal. Okay, so it has nothing really to do with the titration. It is the point where the indicator changes color. So it's kind of like an endpoint, but we don't call it an endpoint because endpoint specifically refers to a volume in a titration. Okay? So keep all those different points straight in your head, if you can. Now, this little equality here, the fact that the acid and the base form are equal, leads us to something else that's quite interesting. If we write our equilibrium for the indicator, there we have HIND in equilibrium with H plus and IND minus, we get a Ka that is equal to H plus times IND minus over HIND. At the transition point, the TP, what is true? No. At the transition point, the concentration of the acid form of the indicator is equal to the concentration of the base form of the indicator. So that's what the transition point is. That's when color A is equal to color B. If that is true, then at the transition point, what can we do with the Ka formula? We can cancel out the IND and the HIND. And what are we left with? We're left with Ka is equal to the concentration of hydrogen. And that is true at the transition point. What that means is if you know the Ka of an indicator, you know the pH at which it changes color, because you know the concentration of hydrogen at which it changes color. If you know the pH at which it changes color, you can find its Ka. Okay, so we can go back and forth between the Ka and the concentration of hydrogen at the transition point, which is the same as pH at the transition point. Well, or it relates to. So, Ka of the indicator is equal to H plus at the transition point, and pKa of the indicator is equal to pH at the transition point. And that allows us to do some calculations. We can go from Ka to hydrogen at the transition point, and from there we can of course use the formula. What is the formula if you go from hydrogen to pH? Negative log of hydrogen, and then we can find our pH at the transition point. You'll notice that little TP down at the bottom, that means at the transition point. If you know the pH at the transition point, you can find the H at the transition point. How do we go from pH to H? What is the formula we use there? Yeah, H plus is equal to the antilog of what? Negative pH. What is another way of writing that? 10 to the power of negative pH. Okay, so you can use that formula there, and you would get your Ka. And how could we possibly find this pH at the transition point, well, we're going to use page 7 of the data booklet to find that pH. So if you can turn to page 7, you'll see that it lists the indicator, it lists the pH range at which the color change occurs, and it lists the color, what the color changes from and to. And the very first one on page 7 is methyl violet. You'll want to have your booklet out, because even though I've got this here, your next one you'll be doing on your own. So for methyl violet, this is how we read this. We say it changes from 0.0 to 1.6. That is where it transitions. And so any pH below here, it's going to be yellow. Any pH above 1.6, it is going to be blue. And when we have a pH in between these two, it is going to be what color? Green. I am never going to give you the value 1.6 and say, what color is it? And make you be like, oh, is it green? Is it blue? What is it when it's right on that? Never. I'm never going to give you 1.6. I will give you 1.5 or 1.7. Does that make sense? Okay. And I am also not looking for you to give me shades of green. If your pH is 0.2, I don't want you to be like, ooh, that's probably yellowy green, right? Lime green. No, no, no. If it's anywhere in between 0 and 1.6, it is just green. Okay, don't get fancy. Yes? If it's 0, it's green. I will not give you 0. I will either give you 0.1 or or minus 0.1. Yeah. Okay, so I'm not going to give you those ones on the end, right? Because it causes too much confusion. Yep. So for methyl violet, we can call that HMV, which is going to be the yellow form of the indicator. And we've got MV minus, which is the blue form of the indicator. And here's our little pH scale here. So above 1.6, we are blue. Below 0, we are yellow, and we have the HMV. And then in between 0 and 1.6, we are green. So if you have a higher H plus concentration, hopefully that should be fairly obvious that if you have high H, it's going to be more HMV. And if you have low H, you're going to have the unprotonated form because there's not as much H there. Does that make sense? Yeah? And don't forget, high pH means what about hydrogen? High pH means low hydrogen, and low pH means high hydrogen, okay? Okay. So the actual transition point where the two are equal, okay? So that would be where the transition point where concentration of HIND is equal to the concentration of the base form, IND minus, occurs exactly at the midpoint of that pH range. So if we look, our pH at the transition point is at the midpoint between 0 and 1.6. How do we find the midpoint between 0 and 1.6? We take the average. Okay, so we take 0 and we take 1.6. Where's my mouse? That's odd. So we take the average, we take 0 and 1.6, and we divide by 0.2, and we get 0.8. So that is the pH at the transition point. Do you remember what else that's equal to? pKa. Okay? So there's actually two ways to solve some of these problems. First of all, you would find the pH at the transition point by averaging the two numbers. And then, if you're asked to find the Ka for methyl violet, let's remind ourselves that at the transition point, the base form and the acid form are the same, so they cancel out. And so we now have the pH at the transition point is 0.8. We can use hydrogen is equal to 10 to the negative pH. That gives us 10 to the negative 0.8, which gives us 0.2 molar. That is our hydrogen ion concentration. And what is the hydrogen ion concentration equal to at the transition point? It is equal to Ka. So you can go from pH at the transition point to H at the transition point to Ka. That's one way of doing it. The other way of doing it is you can go from pH to pKa to Ka. pH to pKa is easy because the two are equal. And then to go from pKa to Ka, how do you do it? Ka is equal to 10 to the negative pKa. Okay? And so you would just, and the math is all the same. Your choice, whichever you prefer. Okay? And you guys are going to try this one on your own. What color is the acid form of phenol red? What color is the base form? What color will it be at its transition point? And then find its Ka. What's that little arrow doing there? What am I looking for next? Sig figs. How many sig figs should we have? Oh, how many? 1 sig fig. Because remember, in any p-value, significant figures are only after the decimal. So that's going to become 5 times 10 to the negative 8 is our Ka. That's as far as I got with my other block because they asked a bunch of questions about the homework and the review. So would you like to work on the review? Okay, you have time to work on the review. Yes. Yes. Probably have a quiz for you as well. Let me see if I can find that. Yeah. Here you go. Did anybody need a copy of the review? Everyone has one? The review for the test? Yeah, okay. Good, good. And your homework, of course, is to study for your quiz tomorrow. I expect great things of you.